Hi, my name is David Hayes. This is my presentation about the lessons I learned while using Dask for satellite image processing. I am a software developer at the University of Wisconsin-Madison at the Space Science and Engineering Center. I've used Dask for about the last 4 years as a Pytroll developer on the Satpy and PyResample packages. I'm also a member of the Pangeo community, working with X-Ray and Dask and other packages that the Pangeo community is concerned with. I have contributed to Dask everything from documentation formatting issues to fixing performance regressions in the threaded scheduler. I also try to provide help to users who post on the Dask Slack. A few disclaimers about the lessons learned that I'm going to present. I'm not presenting them in any particular order. They may not apply to your work. These lessons were learned as part of developing the Satpy and PyResample libraries, not as some data processing script. These lessons are focused on performance, which if you're using Dask, that's probably what you're concerned with. If I miss anything, it's because there's a time limit on this presentation. I could talk about this stuff for hours. If you want to know more about Dask and what you should be doing or what you should avoid, I highly recommend checking out Dask's best practices document and their documentation. And lastly, due to the nature of this talk, it's going to sound like either Dask doesn't do something right or I'm complaining about something, but Dask is great. There are so many things that I could not do if it weren't for Dask. So before I get into the lessons, I thought I'd give a quick overview of Dask for those of you who don't use it on a daily basis or aren't super familiar with it, just so this talk makes some kind of sense. In the left diagram, we kind of have our traditional NumPy operations where we might have a single 2D array and we want to do some operation. That array gets processed in one CPU core and then we get some result. Say we're adding 1 to that array. What Dask tries to do is it takes that large array, splits it up into smaller arrays, in this case 16 chunks of 2500 rows by 2500 columns. Dask will give each of those chunks to a CPU core, and they can process then in parallel. Also, because we probably have less cores than we have chunks of arrays, we're using less memory because we're only processing one chunk per CPU core at a time. So there's less data involved at any single time. This allows us to do out-of-core processing, where we can, over the course of processing all of these chunks, process more data than would have fit in memory on our system. Depending on how much memory we have. Dask uses lazy operations. When you add or subtract or do other NumPy type operations to a Dask array, you are adding tasks to a task graph, like on the upper right here. Each grouping of these tasks represents the processing for one chunk of that array. As you add more operations, you add more tasks, and you get a more complex Dask graph, like in the lower right. Dask will take each one of these circles, it will give it to a worker or a CPU core, and process one of those at a time and just keep on chugging through each of those tasks until it's finished. It does not actually do any of this computation until you ask it to. It's just building up that graph, so when you actually want the results, you have to call functions like .compute, .persist, or you have to convert your Dask array into a NumPy array. And that's how Dask works. So, lesson 1. We talked about that Dask graph. In general, when you add more tasks to that graph, it's going to take more time, but the problem comes in when you add more tasks than are necessary. If you can avoid adding a lot of tasks, you can avoid the about 1 millisecond of overhead per task that Dask adds to your processing. So on that more complex graph that we had in the previous slide where there's sines and cosines, looks like on the left for one chunk. If we can put all of that logic into a single function, we can then give Dask this function using the Dask map blocks call. And then our graph goes from what's on the left to what's on the right. Fewer tasks. We didn't lose anything because we weren't using any of those intermediate results in that function. For small operations or a small set of operations, this isn't a big deal, but for a large algorithm, this can actually save you a lot of performance. Lesson 2, Beware of unnecessary broadcasting. So this is the NumPy array broadcasting idea, where you have arrays of different shapes or dimensions, and NumPy, or Dask in this case, will do what it has to do to combine those arrays when you try to add or multiply or do other operations with them. So what I'm identifying here is this block of code is the same as it was in the previous slide with the sines and cosines, but I'm changing two of the inputs to be generated from two 1D A-range calls and then a mesh grid call to turn those into 2D arrays. So something fairly simple, but it makes our Dask graph look like at the bottom of the slide here. So there's a lot of horizontal lines going here, and this is a very simple operation. So all these horizontal lines are telling us there's a lot of interconnection between all these tasks, but based on the code, this should be fairly simple. This amount of interconnection for something so simple usually tells us that Dask is going to have a hard time optimizing this graph and doing things in a good order. What we can do is try to consider using map blocks to generate that 2D or ND array directly in a map blocks function instead of doing this A-range call with mesh grid or any similar operation to that. And the reason I have this on these lessons is because in a Pyre sample case, when I was working on it, we had a Dask graph that looked like this, where it's very wide and spread out, and there's a lot of horizontal lines of interconnected things. It was using a lot of memory. By doing a change like I suggested with the map blocks call, we changed to this, so a lot less horizontal lines, and things are much more vertical. A single chunk kind of is all in its own group, and it performs much better, saved us tens of gigabytes of memory. Next lesson, beware of AutoChunking when you want to combine arrays together. So here I'm creating two Dask arrays with AutoChunking, which means Dask will decide what's a good chunk based on how much memory it will use, but that takes into account the data type. So here I have a 64-bit float and a 32-bit float. You can see from the results of running this cell that they have a different chunk size. To work with these arrays, to combine them together later on in operations, Dask has to do rechunking to combine them. That's an extra task, that's an extra operation that didn't need to happen if we would have just made sure that they were the same chunk size. If you do more complex things like throwing these arrays into a map blocks call, map blocks will actually work until you try to compute things because it doesn't know how to combine the chunks. It's just something to be aware of, and it goes along with that idea of adding more tasks to the Dask graph than are needed. Lesson 4, this is kind of a very high level when you're thinking about using Dask kind of idea. Some algorithms are not Dask friendly. Simple operations like A plus B, things that are one-to-one chunk operations are very friendly. Things where more complex things like you want the first chunk of A to be combined with multiple chunks of B, that may require doing some fancy custom Dask graph creation, which is possible, but it is more complex. But then you have algorithms that are doing things with fancy NumPy indexing or complex data structures like KD trees. These are the least friendly. You might be able to make them work as is with just some custom graph work. You might have to choose a completely different implementation of the algorithm you're using just so it is all Dask friendly, pure Dask. Or you can cheat and wrap things in a Dask delayed function, which may cost you performance because you end up loading all of your data all at once. So there are just some things to be worried about if you're thinking about converting your code to work with Dask. I should also say that you should look into Dask utility functions or Xarray or NumPy or some other third-party library. They may have utility functions that make some of this stuff easier, like performing reductions or mapping functions to different chunks or doing group bys. There are a lot of people working on those types of problems. Lastly, lesson 5, to use or not to use Dask. I said it before, check the best practices for Dask. They mention a lot of this stuff and what you should think about. They also have frequently asked questions. You can do an internet search for people who have had similar problems and have tried to use Dask and what they ran into. You also have to consider developer time versus hardware cost. It's going to take time to make your code work really well with Dask, whether it's optimizing or just learning all of the features and functionality that Dask provides. If you have extra money in your budget and you can throw more memory, more CPUs at it, maybe do that. Maybe that's a better use of your time. Also, I talked about Dask arrays only in here, but Dask has other interfaces like data frames and their futures interface. Those are other things to consider that maybe work better than using Dask arrays directly. So that's the end of my talk. The takeaways are that you should avoid adding unnecessary tasks to your Dask graph when using Dask. You should definitely read the best practices. Dask won't solve all your problems, but it is still great, and it does a lot for you if you can make it work for you. My Twitter and GitHub handle are here, as well as URLs to the Satpy, PyResample, and Dask projects, and the Pytroll community website as a whole. Thank you.